Scott, and this is the first lesson of topology and geometry, or differential geometry. And today we're going to talk about math models, theories of everything, and Euclidean space. Fair enough? So, since it's the first class, let's say a few words about the class in general, what to look for. I'm Professor Scott Baldridge. I profess. That's my job. And you can visit me in 380 Lockett Hall. A little bit about me. I've been a professor for a while. I study gauge theory and four-manifold theory, Calabi-Yau's, knot theory. These are the range, kind of the range of things I'm thinking about. We'll get into all that good stuff as we get into the class. I'm going to have office hours right after this class, so from 10:30 to 11:30. You can come and ask any question. That's your time. We're going to use this book. It's called, everybody refers to it as Bredon, so I'll refer to it as Bredon, Topology and Geometry. And if you want to follow me on social media, you can go be part of my Twitter followers at Scott Baldridge. There's a bunch of Scott Baldridges. Facebook, you have to put a J because I'm not the only Scott Baldridge. But for graduate students, I would recommend LinkedIn. That seems to be where all the professors hang out. It's weird. Like this is where teachers hang out. This is where media, journalists, hang out. This is where professors hang out, and this is where I hang out. Okay. All right. So I'm going to do what's called a flipped classroom structure. Have you ever heard of a flipped classroom? It's where the modern day flipped classroom is you go watch a video and then you come in and we discuss the video, or we discuss something about the mathematics, or we do examples instead. I'm going to do it old school. You're going to go, instead of watching a video, you're going to read. That's the way that we used to do flipped classrooms. So I'll ask you to read and keep on top of that. That will give me more opportunity to discuss more of the other salient issues that we needed to discuss. And in particular, today, the whole talk for today, for the most part, wraps up in explaining one sentence out of the main section that I'm going to ask you to read tonight. So I don't want you to read that section and then skip that one sentence, not understand what the point of this all is. Okay, so how do we do most math classes? And it's not really going to be an exception here, but in the nuts and bolts of it. In the nuts and bolts of the classroom, we're going to be talking about definitions, theorems, examples, all the same things that you've grown up, known, loved, experienced in the past. But unlike those classes, I want to cover something more in terms of unlike those classes, I want to have a theme going throughout the whole course. And it's best to start the theme right now. And the theme is the way I think about math versus, it's going to emanate from the way I think about the mathematics versus that kind of standard procedure of understanding mathematics that you're used to as a student, right? So I'm going to start with philosophy instead. Math is going to be the tools for me to investigate the philosophy. So we need to start with what types of questions I'm going to be interested in, and we should be interested in. So here's my questions. Ooh, I should go over here. And the first one is, can we find a mathematical model for the universe? Let's not just do like something small. Let's just go for the whole thing, right? Okay? So for objective reality. And, well, that's a loaded question, right? Like this. So what could I possibly mean by that? So give yourself some space here, because we got more questions. But what do I mean? Oh, goodness. So part of the fun of teaching this course is I get to blow, I get to destroy all the myths that you got used to while you were going through your undergrad and your K-12, and because you think you know mathematics, but and it's not your fault. I'm not saying that you think you know the mathematics, but what you know is a version of a set of ideas that all your adults, all the elders, kind of looked at you and said, "You know what I mean." Wink, wink. You know what I mean. And you got used to those ideas because they told you that you know what I mean so often, right? So let's start destroying some of those myths, and let's go after the real, what the mathematics really is. And good news, the myths are there, but they're usually a layer deeper than you're used to start looking at. And then when you see that this is what the mathematics really is, then you see, oh, all that nice mathematics that I did learn, that's not changing. That's all still there. You didn't lose anything. But now you should have a little bit more of a clearer picture of what the objects are that we're playing with. Fair enough? So, first of all, what is a mathematical model? Hopefully someone's explained that to you. But if not, let's build one. So I've got a tree, and an apple falls from the tree. Oh, that should sound very familiar. And I want to model that. So here's my reality. And here's my mathematical model. And I should see certain things happening here corresponding to certain things that happen there, right? And vice versa. But already we see that there's a problem. Can we name some of these problems? I'll give you a hint. Let's see. Let's think about mass of apple. That's usually, I looked it up yesterday, it's usually right around 136 kilograms, or kilograms, 136 grams. Kilograms would be huge. I'm making jokes and I don't even know it. Okay, 136 grams, we agree, roughly speaking? What's my problem?
There's a lot of things that are 136 grams besides an apple.
Sure, but I'm trying to model an apple here.
Okay.
So I've got I've got a specific apple. Do we all agree that you can imagine the apple, it's sitting in the tree, it falls down? That's that apple I want to model. I go and I put it on a scale, and it reads 136 grams. What's my problem?
Maybe reliant on a previous model.
Huh?
Maybe reliant on a previous measurement. So do you trust the gram to be
Do you trust the grams? That's a good question. You see what I'm saying? We need to go, let's just take it all the way back, right? Like, what does it mean to measure? And let's suppose that the measuring device is accurate enough. It still reads 136 grams. Now what's the problem? Did you ever have this conversation? There's a problem. What's the problem?
Yeah. What is a gram?
That's going really far back, and we will address that issue. That's a good question. Okay, but prior to that, now we're just talking about what's actually happening in reality versus what we're trying to model. And I've just written 136 grams, and go ahead.
My name or?
No. Someone had a question? Oh, okay.
I was saying that to even think about the mass, sorry, we are kind of presuming that mass has something to do with our model of gravity. Like, what if something else is the essence of gravity that we don't know about?
So we're going to assume, we're going to start to make some of those assumptions, okay? I'm just talking, so this is where Newton kind of launched his career, right?
So actually I will go back to the Wikipedia itself. So what he does, so he defines these stuffs, mass and everything, and then he says that a particle is Euclidean point with a mass. So it is like approximating something with what he already knew.
So this is going to be part of our model. We're not going to worry about the fact that the apple's taking up space. We'll think of it as a point mass.
Yes.
Okay, so that's starting to get at what do we do when we model? And the first thing we do is we abstract. And the thing that most people misunderstand about abstraction, they think, oh, if you abstract something, it makes it harder. It's the opposite. It makes things simpler. Abstraction is a simplification of reality. Reality is the messy thing. We're going to abstract away all the difficulties. So one of the things we will abstract away is we'll only think of it as a point with a mass. Do we see that this doesn't, the mass of the apple is not 136 grams exactly. It's got to be bounded between, so in reality, this is like maybe 135.99 and maybe 136.01, if we're lucky, right? And oh, by the way, suppose you could write it out to 25 decimal places. It should be really fantastic to have it. But now you're getting into the quantum level, right? And so at the quantum level, it's actually probably, the actual mass is actually changing as there's air pressure hitting that apple and so on. So there's no way, the point is there's no way we're going to pick up really what the mass is. Just only up to some sort of bound. Okay? But over in the mathematical model, it's a beautiful, balmy 136 grams, period. It's exact. Okay? So we got that. Now you got the idea. Gravity of Earth. Probably need that, right? And for us, in the model, it's, oh, look at it. It's 9.8 meters per second squared. How lovely is that? And it's exact. Over here, it's, and I looked this up last night, it's, ooh. Changes.
Is that specific to our region? Or is that
This is all over the Earth, right? It's bounded. This is like the smallest it gets. This is the largest it gets. So we're somewhere in between there. But in the mathematical model, everything's pretty. See what we're doing? How about what's another one that we could think of? Initial position. It's exactly, I'm just making these numbers up here. Exactly 4.9, I do it for a reason, 4.9 meters. So this is 4.9 meters. And over here, no, it's not 4.9 meters. The branch, maybe there's some wind and the branch is going up and down. So when we make the first measurement before we let the apple go, what's happening there? It might be between 4.8995 and meters and 4.9005 maybe meters, something, maybe it's varying. And then if you got all the way down to the quantum level, then well, what are you even measuring? But over here in the model, there's no problem. We just declare. You get the point. There's initial velocity. And let's say that that's 0 meters per second. And over here, it's bounded, right? So what have we done over in the model? Huh?
Do we want to calculate when it hits the ground?
Yeah, in the model, there's in a mathematical model, you can ask all sorts of questions. One of them is the time it takes for the object to hit the ground, for the apple to hit the ground, right? We've all done this. This is why I'm starting off with a simple idea here, right? This is about 11th grade, 12th grade, right? I'm not pushing hard stuff on you right now. But we did, in the mathematical model, we ignored a whole bunch. We just ignored it. So we ignored. And so this is why math is so much fun. Poor physicist has to think about everything else. Mathematician can just say, well, I'm just creating models. So what did we ignore?
The dimensions of the apple.
Yeah, it depends, right? Do you need to know the dimensions of the apple to go after that theorem that we want, which is the time it takes for it to? Not really. We can ignore them. Yeah, so we can ignore. But there's some very important things that we actually did ignore here.
Variability.
Air resistance.
Huh? Air resistance, yeah. Definitely ignored that. What else did we ignore? Like, by the way, if we find out even, what the acceleration of the Earth is at the right here or right underneath that apple tree, it's still bounded. It's still it's a much tighter bound, but I can't get exactly that. Right, so I'm going to ignore that too, right? So I'm going to ignore the tolerances, any tolerances over here. What else? Rotation of the Earth. That's if you want to go over to LIGO, just 30 miles down the road, you just got to start worrying about and you're trying to do very, very delicate measurements, yeah, now you got to start worrying about all sorts of things. Like I said, those poor physicists. Okay, what else did we, oh, atomic fluctuations, if you really get down to it. You know, there's a bunch of things that we're just flat out ignoring here. Okay, so here's my, now with all that information here, my mathematical model looks like this. Sorry, it's not actually the model. The model uses F equal ma, right? But then if you get the equations of motions for it, you would see that S sub t is just what you would expect. So the height at 0 is 4.9, and it's accelerating at it's got an acceleration of 9.8 meters per second squared, and if you work out those equations, you get the standard fall problem. Oh, what else do I need? Make sense? Okay. Now that's my model. And in my model, I can write down theorems now. So we're getting right to what mathematics is. So what's a theorem? Graduate students who've been solving theorems for years and years and years. What's a theorem?
If you have hypotheses, like, then you have a conclusion. In a way, I don't know, I'm kind of missing things in between, but if certain
No, you've roughly got it right? Like a theorem is an if-then statement. That's what a theorem is. It's just if X, then Y.
So the thing is that you apply the laws, mathematical laws you could deduce from axioms.
Which are deduced from axioms. So now a theorem is, so that's what you described as a mathematical statement, right? So I can give you a mathematical statement. 2 plus 2 is equal to 5. Perfectly valid mathematical statement. So what's wrong with my statement? Is that a theorem?
It's false.
Ah, it's false.
Are you asking, well, it must first also be true, but then again, we've established some amount of import on it to not classify it as a corollary or a lemma or a...
Oh, no, all theorems, all corollaries, all lemmas are theorems. So, I'm generically a theorem is a if X, then Y statement. Well, wait, a mathematical statement is an if X, then Y. Right? It's not a theorem yet, because I just gave you a mathematical statement that's not a theorem. So what do we need theorems?
It should be true, in the sense of axioms. So we assume that something is true, then we should be able to deduce it from those.
Yeah, very good. So would it be reasonable to, and what are axioms?
So axioms are self-evident truths. So there are two in sense of Euclid and these people. So there were axioms and postulates. So axioms were those statements like fire is hot. So if I tell this to my pupil, then they will not question it. But
Okay, so
yeah.
if I'm hearing you right, you're going to give me a set of sentences. A mathematical statement is a sentence, right? It literally is this. In first order logic, it's a sentence. If X, then Y. And then you're saying that I'm going to, out of all the sentences I can have, boy, this is starting to sound like philosophy again. Anyway, if out of all the sentences I could have that are mathematical statements, that include things like 2 plus 2 is equal to 5, the assertion that 2 plus 2 is equal to 5 is a sentence. Not all of them are what we would like to call true. And so we establish a few of them that we say, well, let's just call those true. Because they sound like they might be true. Like if you have number system, you can and you add A and B are numbers, and if you add A plus B, that's equal to B plus A. That sounds reasonable as a truth. And so then we'll say, well, let's call that an axiom, because that's a kind of a fundamental statement in a set of all statements. So I'll just declare that to be true. See how that's reasonable? Now in first order logic doesn't care. There's all sorts of wonderful logics.
There are false statements that we often use in mathematics because that's are very useful.
Yeah.
Like the value of pi is 22 by 7.
Oh, that's an approximation,
Yeah,
right?
that's what I mean. It's something, this kind of thing.
It's something that happens maybe over here, right? No, but now I'm actually in the mathematical model. Over here, this is all messy. This is reality. Over here, it's pristine. It's pure mathematical model. Okay? So before I can write down a theorem here, I got to know what I'm writing down. And we've got that you have to do a proof, and that the proof has to include, a theorem is a mathematical statement with a proof. You can't have the theorem without the proof. Otherwise, it's just called a counterexample. So 2 plus 2 equals 5 is counterexample. It's not going to work. It's a false sentence. It's perfectly okay to say, it's just false. By the way, it's the false ones that make the true ones valuable. If everything was true, who would care about writing down any sentence? It's the fact that 2 plus 2 is equal to 4 that's unique. Out of all the sentences, 2 plus 2 is equal to 4, 2 plus 2 is equal to 7, 2 plus 2 is equal to negative 8, 2 plus 2 is equal to pi. All those false sentences, but only one true one. And then we look at all those sentences and we say, well, there's a particular set of nice ones. Let's call those axioms. And then can we derive, and then in those statements that we assume to be true, can we then prove, using first order logic, other sentences to be true? And when we do that, we've taken a sentence that says, if A, then Z, and then we have a proof underneath it that says, if A, then B, if B, then C, if C, then D, if D, then all the way down to if Y, then Z. And I've got a sequence of linked true sentences. Yeah. To get me if X, then Y. Okay, there's lots of people who've thought about that. Right? There's Platonists, and there's the Kantians, and there's everybody wants to know, well, what does it mean to have something that's true? And the best that mathematics can, and from a philosophical standpoint, right? That's what we're talking about. And they get themselves all tied up into knots. Meanwhile, the mathematicians and the physicists are having a gay old time just solving problems. We don't really worry about these types of philosophical problems, and I'm not going to either. But you should eventually, during your graduate school, start learning about those things. Okay. So inside a mathematical model with a given set of truth statements, truth claims, some of them which I'm going to assume are true, and then others of which I can derive to be true from those initial set. Yes? All those truth claims that include things like the axioms of a ring or a field, let's assume all those. And let's assume all the other beautiful axioms for doing algebra. Then I can write down a truth claim here. And my mathematical model includes all those other pieces of the model plus this piece. So I'm going to assume this, and now I can actually write down a theorem. there's a statement. Is it a true statement? Look, I can give a proof. You can't give a proof over here. I just observe. But I can do a proof here. I say, well, it hits the ground when S is 0, so it's at this point. And I do the usual thing that we all know how to do, and I'm not going to do it. Right? You start solving the equation. Start solving the equation. But solving the equation is a set of if then x. If x then y. Every time you solve an equation, you're proving a theorem. So I get to the point where I get to now, which one can I not use in my model? I can't use this one in my model because I had to make sure that my time was starting at a particular point where there was no apple falling. So D can't be -1. And so then we conclude. Here, look, I gave a proof. There's my model. Very simple. Here's my model. Here's my reality. In my model, I can write down truth claims. They're absolutely true. Over in reality, what can we say? Just observe. The best that my stopwatch can work, I observe that it's between there and there. Okay. So I would call this an absolute truth claim, just to make up terminology that you don't have to remember. Fair enough. But absolute truth claim, it's in the model. The mathematical model is exactly 1 second. So 1 second exactly. I'm going somewhere with this. Over here, what should we call this? So this is still a truth claim, right? This is the part where Kant gets all knotted up about, can you have truth? Can you have objective truth?
It's like almost 1 second.
And he gets all bothered by it. He says, oh, you can't have any objective truth. And you know, we're just lying to ourselves. And Descartes says, I think, therefore I am. And, you know, there's an objective truth. And blah, 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 blah. And they get all, it must be fun to be a philosopher. But we don't have to worry about these things in math and physics. We actually have what we can say are absolute truths within the model. Right? So remember, the model includes all the axioms of the field of the real numbers and blah, 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 blah. So we can do all that stuff with if-then, or we can verify each if-then as a true sentence, and so therefore that's true. That's a true sentence. But over here, it's a little based on measurements, right? So I would call this a tolerance truth claim. It's based on tolerances. So maybe go like that. And that just says between. It's between. Yeah, but it's still true. Still, you know, if you get really careful about your tolerances over here, you're still giving a truth claim. That's what I'm saying. It's like all those philosophers can. Well, it was good that they thought about that stuff, but it's something that the physicists and the mathematicians really don't. Because if we want to blow a rocket to the moon, I can use the mathematical model, and if I'm careful about my tolerances, I can determine almost to the ounce the amount of rocket fuel I need. Get there and back. In fact, we've done that a few times. So, and I didn't have to send some poor schmuck out into space going, well, we're just going to put a little bit of fuel on board and see if you can get back. We didn't have to do that. Oh, we made a mistake. Sorry. Enjoy your rest of your life floating out into space. We didn't have to do that. We could just build our model, get some truth claims in our absolute truth claims in our model. Those absolute truth claims with careful understanding of the tolerances gave us what we needed to put on board, and lo and behold, it works. Yay. So we don't, mathematicians, and we don't really get all that worked up about. Jose?
I read a nice example in context to this. So once there was a bus that fell in the river, and computer, calculated all the tensile strength and everything. But when the crane went to lift the bus, it fell into the river because they didn't calculate that. They didn't thought that the bus will have a water filled inside it.
Oh, you brought up an excellent point. So he's talking about we did go do the calculations and it failed.
Yes.
Okay. Yeah, that's a good, let's point that out too. Your mathematical model is only as good as it predicts what's actually happening in reality. We agree? So that's a sign of, if you were to label what could be a good mathematical model, you would say a good mathematical model allows me to make predictions, and in those predictions, when I go to observe what happened, that's what's happening. Okay. Excellent. Yeah. And people put forward mathematical models all the time, and they say, yeah, this model is going to work. And sometimes they do, and sometimes they don't.
Mostly happens in economics that when
Yeah. There's
lots of model clashed. Yes.
not dissing on any particular subject, we won't, but there are subject areas where but they're proposing. They're saying, look, here's a mathematical model. Let's see if this mathematical works, and then it doesn't. It works until it doesn't, right? Yeah. And it happens in physics too. And then when it starts to kind of go a little haywire, people start to go, well, what's going on? Right? And that then encourages more understanding about how do we change our model to incorporate this new idea. So that's all part of this wonderful thing that I basically spent the last 40 minutes explaining to you, which is called science and the scientific method. And here's the relationship between what we observe and what we're trying to do. And every scientist is basically trying to develop a model. Some models can be spoken with English, but most of the models nowadays are spoken with mathematics. So yay for mathematicians, because that means we have a job forever. Oh yeah, go ahead. Yay for us. Now I want you to do something different. Now I want you to imagine and it's a thought experiment. Imagine that you could build a model a mathematical model that was exactly objective reality. Like, you kept doing the tolerances down to the point where the tolerance became 0. There was no difference between these two numbers. And it was exactly 1 second. And suppose we can't measure that. We can't. By the way, that takes us out of the realm of even being able to measure. So, we're not talking about stuff that we can actually do. But that doesn't mean that mathematicians and philosophers and scientists can't imagine. So, imagine that you get 1 second. Whenever you get 1 second over here in your model, you get exactly 1 second here. You get exactly 1 second there. For every calculation you want to make. Kind of cool. So I guess I'm going to use this over here. So imagine we've got a math model, and it's 1-to-1 with objective reality. So if you have a truth claim over here, it's no longer a tolerance claim over here, it's a truth claim here. So an absolute truth claim here corresponds to an absolute truth claim here. One second. Perfect. What type of model, what would that model have to include? So model must include name some things it has to include. We're talking about the perfect of the perfect models.
So, it has to be like things in reality should be correspond with mathematical objects.
Exactly. So what are some of the more famous mathematical models that help us understand reality? So, for example, a really good model is the one that predicts when the next lunar eclipse will occur. That's a fantastic model. I remember being in, I think it was 1979. I was a young kid, and the TV announcer said, in 2017, August 21st, 2017, there will be the next lunar eclipse. And sure enough, that was some 40 years later. That's a pretty darn good model that gave them that answer. See what I'm saying? What model is that? Well, come on. We have things like classical mechanics, general relativity, this is just the limitation, or this just is going to be the limiting of general relativity to kind of the Euclidean. What else? Yeah, quantum mechanics. Now you see it's going to get difficult, right? Better explain things like dark matter. Energy. Oh, yeah, we are so clueless. Why is it called dark matter? Because we don't know anything about it. Not really. We just know it through our calculations. We know it's there. Okay, so whatever this perfect model has, it better tell us some information about that. Do you see the trouble? We're not done yet, right? There's a lot of other things that may be hidden from us even right now. Just gone. We aren't seeing it. Yes?
So back in my first year of physics, I asked my teacher what is energy, and he had a really hard time explaining that. So I'm asking you that to see what you say.
It's mass times velocity squared. Okay, so let's call such a model a theory of everything. Now there's the standard model, and that doesn't include gravity, but the theory of everything should include gravity, explanations of gravity. And what we have to know is that you have to understand with a quote theory of everything is that it's not going to give you, the cost to get in quote exact value is so great that you would still use tolerance truth claims. Does it make sense? Like to calculate every photon and every electron and every quark as it moves, as it's moving of the apple, as it's floating down to the ground. If you had a theory of everything, that could give you an accurate answer as to the exact moment that it fell, it hit the ground, and what it meant to hit. There's all sorts of problems there, but that calculation would take a computer the size of the universe maybe to do. Like the cost to make that calculation is so great that we'd never ever use it. So we're still in the world of truth claim, and tolerance truth claims, because that's the way to reduce the cost. Yeah. But that's not the point of a TOE. TOE would be more to get at the structure of the universe, answer basic questions about the universe. Yeah? Some of those basic ones would be, and this will sound familiar, because you asked about energy, but before you get there, what is time? A TOE should give you some information about what you think time is. A TOE model. Remember, a TOE model is this thing here. Reality is this thing here, and we're assuming there's a one-to-one. What else? Why does it have a direction? Hasn't that ever bothered you? If you've probably had some knowledge of time, space-time, and there's this thing called space, and there's this thing called time, and space, doesn't matter if I walk this way in space-time or walk that way in space-time, I have freedom to move in either. Somehow time, I'm always forced to go forward. That's a problem. And TOE should explain that. Well, what else? Now, what is the mechanism behind entropy? Should explain what entropy is. Oh, by the way, these are kind of the same thing. Time and entropy, yeah. Yeah, it's the feeling of time. Things degenerate, or entropy increases over time. It's kind of equivalent statements. I mean, you have to be very, very careful, and there's certain things that are, but I'm just saying roughly at this point.
Should the theory be able to explain whether we live in discrete world or continuous world?
Yeah, that's another thing. So what is space? You talked about time. What about space? Oh, why is there 3 dimensions? Are there more? Just can't see them. Is the universe super deterministic? Am I on 5 here? Yeah. I.e. a clockwork or universe or mechanistic. Or is it random? Or is it other?
So isn't this question has been proved in negation by John H. Conway in 2006? It's previous theorem.
No. There's still people that, like T. Hooft has posited that he can come up with a TOE that involves a super deterministic model.
But I mean, how can two opposite results in mathematics be true? How can two contradictory results in mathematics be true simultaneously?
That's because okay, here's the problem with all these TOEs. If you have a TOE model, you can't tell if you had 2 or 3 TOE models, I don't think you could ever tell which one you have. So, for example, this is the super deterministic model. Man, that's scary stuff. Now we're really getting into philosophy, yeah? You should have nightmares over this. Because what does a super deterministic model look like? Super deterministic model means that I've got a model, and that if I had a computer that was the size of the universe, it was often called Laplace's demon. If I had Laplace's demon, it could calculate exactly every electron and photon and movement of every particle in your body for the next 10 years, the model would tell me what you're going to eat 10 years from now in the morning for breakfast. That's what super deterministic means. You are just floating through the clockwork mechanisms of the universe that you're living in.
So is this same as Laplace determinism, or is it same as Laplace determinism? Or
Laplacian? You say Laplace?
Yeah.
Yeah, Laplace is the one that came up with the mechanistic universe, right? There's a famous quote where Napoleon asked Laplace, I noticed that you don't have God in your as a hypothesis.
Yes.
And Laplace said, I don't need that hypothesis, right? And what he's saying is that he can explain the same thing that Newton had explained without having to use to invoke God. Huh?
There is also next part of this story that Napoleon said this to Lagrange, and Lagrange said that it was such a good hypothesis. It explains so many things.
Wait, did Newton have God?
Huh?
Yeah, Newton's Principia. So Newton, actually he was atheist, but I mean Newton has God, but it's different kind of God.
It's a different type of God. But he has to invoke so this is the God of the unknown, right?
Yes.
Why was there a lightning strike and destroyed the house? And you say, well, I don't know why, and so you say it was God.
Yes.
God becomes an unknown factor. It must have been God. And then we find out that there's science, and the science says it doesn't. That really wasn't a thing that God did necessarily. But now we're really getting into philosophy, yeah? And the question is the super deterministic, is it super deterministic? And if it's super deterministic, that should scare you. You should be very scared by that, because it means that you are just following a path. You are just a particle on a path that's already been minimized, energy minimizing path, and that path that's what's going to happen to you. And now the point that I was going to make is that you can't tell that you're in that model. Because any type of question or any type of experiment that you decided to do to make that test whether you're in that model would be incorporated by the fact that all the electrons in the experimenter's head were colliding and hitting each other in just the right way to produce exactly the model that he was going to quote, or she was going to quote, create to find out whether it's already there. You can't tell. And what about random? Well, random's got a problem too. There's a problem with random. Random means that there really truly is a random number. It's not like we only have pseudo-random numbers if we want to create a random number type.
I mean, in this sense, like Einstein was someone who was super deterministic, so he said that.
Yeah, it's got to play dice, you know, it's this old question, right? This is philosophy. But what I'm trying to tell you is that if you're going into the job of being a mathematician, you better maybe come to, not right away, soon. You should start thinking about what you're really trying to do. Now, this is the big question, and there's some of you might be applied mathematicians, and there are big questions there too, right? I'm not discounting. This is the purest of the pure mathematical models that you could possibly ask for. Okay, fine. That's kind of the thing I like to do, but LSU's got this great big department with really awesome applied mathematics, and that also is very, very important. So, but the problem with random is, and these all come around this question, is there free will? And wow, that's a loaded question too, so I'll put that in quotes.
What's the difference between random and free?
Well, random means that you actually can have a random number, not a pseudo-random number.
Something like that you can't control, but free will is something.
Yeah, a pseudo-random number, think about it. It really comes down to whether there's purely random or if there's a pseudo-random. Like pseudo-random says that you can never get purely it almost comes down to the same question of can I divide space forever? So these two things are kind of bundled up in almost the same ideas. But suppose that you had pure random numbers. You could generate a completely random number. Well, would you have free will at that point? No.
No,
Then it's your choice to do X or Y or Z is literally happening because of the random choices or random things that are happening inside your head at a quantum level that then emerges as the choice you make. So you are not governed by the I will do X. So either one of these, and this is why I have to say, is there an other? Or is it impossible? That's another good question. Is it just impossible to come up with a TOE? You're not going to be able to do it.
If you think on a small scale, it looks like all the three is true.
One thing I didn't put in here, I should have, maybe here. What is a particle? So I've been talking about electrons and photons and neutrons and what the heck are those? They're not points. A point can't have mass. It's got to be something. See the problem? All right. If we had a TOE, the TOE should tell me what that is. Explain it. It should have a good explanation of what that thing is. There's all sorts of other questions, like it should explain all the parameters that we have maybe in the universe, or explain why those particular things work. There's lots of examples of these types of TOEs that you've heard in the literature and on TV. You know, science geeks just love talking about this stuff. There's string theory, there's quantum loop gravity. There are different models that we are exploring right now. By the way, some of the people are here in the physics department. We're over across the way. Okay. Why did I? So here's my point. So here's some of the philosophical types of questions. And I conjecture, it's a conjecture, that the best, and what do you mean by best, or greatest, and what do you mean by greatest mathematicians are the ones that start from these bigger issues in whatever they're studying. And like I said, if it's an applied mathematics, you also have these big issues. Maybe not as big as that particular type of question, but it happens in any particular realm. You got to relate it back. You got to relate your mathematics. In fact, in applied mathematics, it's great because it's much more relatable back to humans. Whatever you're doing, it's got to be, yeah. So I call myself an applied mathematician, a theoretical physicist. Think about that for a second. They're thinking, I claim that the great mathematicians are thinking about these philosophical questions all along. And maybe I'm wrong. Maybe even the not so great ones are thinking about it. That could be me. But I will say that since I started thinking about those, it's given my life direction. And I now know how to exclude looking for pretty little shells on the side of the sea, on the seashore. I stopped looking for pretty little shells on the side of the seashore for a long time, and now I look out into the ocean. For you, have you ever gone snorkeling? A couple people. So, snorkeling? Means the little face mask kind of thing that you plug in and you can breathe through, and then you swim along the shore. If you've ever done that, and I highly recommend to do it at some point in your life, if you go on snorkeling, the guide will take you out to a place where there's lots of pretty coral reefs and beautiful little fish that are swimming all around. And you see the beauty. And too often teaching math is basically the mathematician showing you being the guide, taking you out to the coral reef and showing this pretty little fish. The issue is that if you've ever done that, you notice that the coral reef drops off and you see the abyss. Like if you go out far enough, you see where it's not, like at the coral reef part, it's maybe 10 to 25 feet deep and you can see all the way to the bottom, but you get out to beyond the coral reef and you get a sense of that's going down a few hundred feet. And it's dark and blue. And so my goal here in this class is to help you not play and search for pretty little shells on the seashore, but to actually be your guide, take you out into the ocean, have you see some of the, you still need to see some of those pretty little fish hanging around the beautiful coral reef. And then if I'm lucky, I can take you out into the abyss a little bit, bring you back. So, I've got 10 minutes. That I guess would cover this in my introduction to the class. where you will see me take you out into the abyss is I'm going to take you, when I take you out into the abyss, it'll be over things that you thought you knew. It's okay. Sometimes I tell my students, especially the graduate students, the reason why you're here is because you ignored these problems. You ignored the questions that other people asked and said, oh, I don't understand what this guy's talking about. It's not fun to think of, maybe that's the reason why you're here. But think about that for a little bit. And then before we start, we have more TOEs to explore. Oh my goodness, this is just the beginning, right? Like, what could a TOE look like? So we'll take a look at some of that. But before we do that, we should have just kind of a basic understanding of this thing called space. And this is kind of one of those spots where, obviously I don't have time to really get into it with only a couple minutes left. But this is a perfect example of something you thought you knew. And it has consequences. So I'm going to call this traditional space. And it's not necessarily objective reality space. These can be completely two different things, right? So here I'm talking about a space that is something that you have heard before. It's called Euclidean space. Okay, so no problem with that, right? So we need Euclidean space. And we need Euclidean space just to build up to what a smooth manifold is. We need a smooth manifold to be the primarization of a potential TOE model. So this is valuable. This will be valuable information here. And so I ask, what is Euclidean space?
You can define it several ways.
Sure, good. And I'm going to take the modern approach. Okay, but what is the standard definition? What's the old definition?
You can affine a space with the concept of inner product.
Oh, that's the modern approach. That's what we're going to do. Excellent. I'm glad you're up on that. What was the original approach? Euclid was not sitting there.
No.
Well, I say I got this inner product, and it was based on the real numbers. And
all the space was Euclidean space.
hmm?
And for him, everything was Euclidean space.
Right.
And he didn't think about it.
So what was Euclidean space?
Collection of points, lines, and figures.
Points, lines, planes,
and so
3 space, right?
he didn't talk about these.
What did he call them? Well, he didn't call them, but what have we come to know them as? What type of terms?
Geometrical objects.
We got a specific name for them in Euclidean geometry. Euclidean geometry's got a list of 5 axioms, right? He says, well, it makes sense that I can measure angles, and so I'm going to create an axiom for that. And if I got 2 points, I can draw what? Yeah, there's exactly one line that goes through it, right? And that made sense, and so those were the beginnings of a model that is called Euclidean geometry, right? But when you start with a point and line in space, what are those? What type of terms are they called? Oh, this is good. I've got 3 minutes, and we'll have a nice discussion about this.
It's spaces, hyperplanes.
No, I mean, there was not that stage, but I mean, as much as I remember, they call it figures, mostly planar figures. I mean, of course, I have read English translation, I don't know what it is.
So if you want to define a cat, you can say it's part of the feline family. But if you want to define a feline family, what do you eventually have to get to? Otherwise, because you can't then say that a feline family is the family of cats.
I mean something which
A little circular, right? So what do you have to eventually come down to?
some kind of anatomy or something like some scientific biological.
Yeah, but then you'd have to define, well, it's got 4 legs. Well, then you have to define what a leg is.
That's the
Yes.
correct
So
characterization for.
So yeah, there is one thing I read that if you continue this, then at one point you will stop or you will have to.
Yeah, either you become circular.
Yeah. Or you
Does everybody see that? Eventually you go down to a definition that circulates back up to one of the previous definitions. Or it stops and you have to say what about that term.
Yeah.
They are primitive terms.
It's a primitive term. It's an undefined term.
Yes.
Yeah, exactly. So even though I'm not quite sure of how Euclid was thinking about them, we think of them today.
Ideal objects.
Well, that's the Platonic, but he was just thinking of them as kind of undefined. Yeah, I know it's a little. He calls them a breathless thing.
Yes.
Yeah. He's trying to define them,
Yes,
but more modern. The more modern mathematicians tend to just say, well, these things we will have a thing called a point. We'll have a thing called a line. We'll have a thing called a plane.
He defined points like something which has.
He tried to, but you don't really define them,
Yes.
and that's the issue, right? But the point is that you get all the way down to your root, and you get to something that you just can't define. You call it an undefined, and then you have relationships between the defined. So Hilbert, I think, was it Hilbert that famously said you could do everything with a bar. You could have given I'm going to blow this up, but given 2 mugs of beer, you would have these things called beer mugs, a bar. Do you remember this?
No, I thought that you were talking about argument. He said that.
It doesn't. Yeah. Huh?
You're talking about the Weaver thing.
Yeah.
Yeah. No. I'm just saying you could use any word you want.
Okay. But
You can use any 3 words you want for point, line, plane.
Okay.
So give me a couple of them. Just give me a couple random words.
He wrote that book, Foundation of Geometry, but I don't remember.
No. Don't do the equation back to the reality.
Oh.
Just to say, we could say point is same thing as a cat. And if you have 2 cats, then you have a dog. And so then you have these undefined term called cat, you have an undefined term named dog, and you say whenever I have 2 cats, I have a unique thing called a dog. And you can just do all the geometry over again, because it doesn't matter what you name these things. The names don't.
It is Hilbert.
So what am I trying to get at? We're trying to get at this thing called Euclidean geometry. Euclidean geometry is this thing in essence, at least in modern times, is an undefined term, this thing called space, and but it's got something called a distance on it. So that if I have a point here in the space and another point in the space, I know that there's a distance between those 2 points. And the distance satisfies a nice property, the triangle property, and so on. So that's where we start. We start right at that. That's the old way of thinking about it, but we're going to build up to the new way of thinking about it, which is what is an affine space. So, to conclude, well, I still want you, well, I haven't given you the reason, I can't have you answer this question yet. So, in Topology and Geometry, in Bourdon, go and read 1 through 62 quickly. Quickly means quickly. You don't have to think about every example and so on. But it should be review for you. It should be a lot of review. And if it's not review, then you got to sit there and think about it just a little bit. And then read section 2.1. So this is basically all of section 1. Section 2.1, read that one slowly. Now that's typical mathematics that you're used to. should be used to. I think it's the implicit function theorem or inverse theorem. It's one of those two. Should be something that you've seen before. Maybe a little newer context, but I still want you to read that one slowly. So there you go, and you do the examples and think about them. And then we will start this on next meeting, which is to explain one sentence in section 2.2. There's one sentence that he just states. I love Bourdon, but he just states it, doesn't really explain it, just assumes that you know it, and we got to talk about that. Fair enough? Okay, great, thanks.